find the minimum of function instead of just having the differential equation here. Okay? Because here you can see that you go down or up. It's a saddle point, so it's not so easy. Okay. Okay, so just to show you that we can, so we have this one, sorry, this one. This is just easy, the standard finite element approach is this. Okay. Now you have this dual approach, is this. So technically there are ways, okay, I'm not going to, there are ways to make discrete vector fields such that they are divergence free to some sense. Okay. And then I can optimize a function, this function phi star, on this, and I can make flux-based finite elements if you want. Okay, this is feasible. Okay. And then I get the flux, and then from the flux I can compute the gradient of mu by the constant model, but because it's the minimum, I know that this gradient of mu, I can, this field vector, which I obtain from k minus 1 times j, is actually an integrable field, and I can get a scalar field out of that. Okay. All right. So this is just one step towards the obtaining the full variational principle, because what we want is to study the transient rate. Okay? So what happens if I want to study the transient form? Okay. So we start from here. Oh, sorry, I just I keep the same thing, but I add this time. Okay, now remember we had define the function, the free energy function of C. Okay, go back here. The pure, okay, here we are in the pure. Okay. So I have this function. My model is described by this function, and the phi c or the phi c star function. Okay. The whole model is described. Okay, I've got two constants, the h and the kappa. The h is in here. The kappa is in here in the phi c or the phi star c form. Okay. And here we are working with the phi star c form. So let's see where. I'm working with this, okay? So there is a typo in the slide, but I changed the notation, so I should have changed it everywhere, but okay, not yet. This is the phi c, so the chi. The old slides was called chi. It's a phi c star, okay? It's a quadratic, this is the one as before. Okay? I just added one term here. Okay? Okay, so here I'm in the uncoupled case for the moment still. So I consider that I have a free energy function of C with the P dots. Okay. It's just this, okay? But okay, I write it. Yeah, that's what it's here. Okay. And if I give you this C, this derivative of C with respect to C gives you the chemical potential associated to the C, okay, in equilibrium situation, but that's what we will consider here. We will consider that it's locally it's always in equilibrium. Could make it more complicated. But what I'm telling you now is that, okay, so I've got a function now of j, but also of c dot. And I consider, okay, I'm working at the evolution problem, okay? So I'm considering that I know c. C is known, so it's not written here, but it's, and I want to define the evolution of the system in terms of the rate of c and the flux. Okay? So I can construct this functional. Okay, if you look at it, this is a linear function in c dot. Okay. I'm going to make it stationary. I'm going to make this p star function stationary with respect to c dot as well as j. J is it's a quadratic function, so clearly it's a minimum. Very clear. Now, with respect to c dot, it's a linear term. So if I minimize with respect to c dot at constant, or if I look at the function of its j, how it evolves in function of c dot, it's a linear function. So I cannot really say it's going to be a maximum or a minimum. But I'm telling you I want it to be stationary. Okay. No, it's a bit subtle because if I fix c dot and I minimize with respect to j, I'm going to get a function where there will be an explicit dependence on c dot, but the j itself will depend on the c dot I've chosen. Okay, so it's a more complicated function. I could try to define if it's a convex or concave function. Okay, but in this case, I'm not trying to do that. Okay. Especially because, okay, I try to find this stationarity of C under constraints. The constraints now are a bit more complicated. I have a constraint between my unknowns, got a linear constraint between my j and my c dot. Okay, I write not, before I was writing only divergence of j, okay, but now c dot is also an unknown field, so I can make a constraint which is involving c dot as well. Okay. So I enforce the conservation of mass as a constraint, and similarly as before, I enforce the boundary conditions, the Neumann boundary conditions. Okay. Okay, so I don't think I'm going to go into. We can do the same thing. Okay, so you have to write. Yeah, it's in here, but okay. So I'm going to define this this Lagrange functional. I got my Lagrange multipliers, which enforce this constraint on the volume, enforce this constraint on the boundary. Okay, just as before. And now I can make the whole thing stationary with respect to this. Okay, so again, the supremum here, I don't really use it. Technically, it's a constraint. Okay, in this case, it's a bit. But it would have to be double or triple checked. It's this way. We don't use it as a supremum. It's just use the stationarity. So I could write stat here as well. Okay, it doesn't really matter for what we do. Okay. So okay, and again, I will have to write. Things like, okay, I want if I want to take the directional derivative Okay, in the order I will have this. Okay, so we're making perturbation of the concentration rate field. Okay, we want this as well. Okay, this is stationary with respect to perturbation of the flux field. Okay, so okay, this is what is written here. Okay, just a slightly different notation, but the same thing. Again, this is always a okay, and then so this one, okay, again we have a function which is linear in C dot here, and we have this term which is linear in C dot as well. So for example, this one will give me so the integral over the domain delta C, okay, which is a known quantity, delta C dot, okay, and then okay, the other part is going to be lambda okay. The only places where delta C dot is appearing is here and here, okay? And this one is just it's just in here, okay? Is this, okay? So I can create a new hat if you want. Okay, so this is, let's say that this okay. So this is why I'm telling you that this tells me that lambda must be equal to the chemical potential computed from the current concentration field. Okay? So we retrieve the fact that lambda is a chemical potential field. Here we have an additional equation which links lambda to C. Okay, if I write the second one, it's going to be roughly the same thing as before. It's a bit of a lengthy one, but basically it's the same as before. Okay, so the if we look. In terms of J, basically, when I add the C dot terms, I'm going to have this extra term, but when I take variation with respect to J, it does not appear. And in the phi star, there is a mu hat C dot, there's no J there, okay? So fundamentally, this is the same as what we just did, okay? Just exactly the same. Okay, so I got, what did we get? We got that A minus 1 J. Okay, K is symmetric, so I can write it in one way or another. Here we have something like this, remember? Okay. And then we had that lambda equal to mu bar okay. This is what we just did. This is the same. Okay, so from here, you know that lambda should be equal to the chemical potential. Okay, this chemical potential should be fits on the domain. Okay, so the lambda is and the lambda should be equal to the chemical potential on the boundary too. And the flux should be such that it's actually the gradient linked to the gradient of the chemical potential. Okay. And this one tells me that okay, you can write it if you want. This is this thing, okay. Again, it's the same thing. This gives me the J should be verify the mass conservation equation, and then it should be equal to the imposed value on the Neumann part of the boundary. So I retrieve all my equations of it. Okay. But again, instead of solving differential equations, I write things as an optimization problem. Okay. So the idea is that, of course, mathematically I'm doing all this operation to tell you, show you that the optimality conditions are identical to the classical equations, differential equations. But we write the minimization because the optimization because we want to use that later, maybe injecting some approximation of the fields and then minimizing or optimizing it. Okay. Then now if I want to put mechanics on top of it, now things become easier because I got a big solid base. So okay, what happens if I add mechanics? Okay, I need to add extra terms which are the classical terms which you can see the elasticity. So now my phi is a function of epsilon and c. Okay. If I ready, I start. Okay. So now okay. Let's take into a function a bit more complex. So there is this. Okay. And okay, with epsilon being I know that. Okay. That epsilon is, I impose, in this case I impose the compatibility equation, the kinematic compatibility, okay? So this means that psi dot is going to be okay, and this is I consider relation giving me sigma in function of c. So in this case I put it explicitly, okay, through the p. And this one is the I call it mu hat because okay, just call it mu, but so this is the chemical potential as function of epsilon and c. That's the one we've seen before. Okay. And this one is the gradient of velocities, the symmetric part. Okay, so formally you see this doesn't change, okay? Just now the psi is different, but it's the same as what I did here. Okay, so this it's a phi c again, but phi c star. But psi dot plus phi c star. Then I've got this boundary term. Okay. If I'm doing mechanics, okay, I also have energy terms forward coming from the mechanical loading. So I need to have imposed traction vectors on part of the boundary, imposed volume forces, they enter into the same two. Okay. So here again, I'm going to say that I've got a known state, so I know the deformation and the displacement. I know the concentration. And I want to find the velocities, the fluxes, and the rate of concentration. Okay? My evolution problem. And what I'm telling you is that this big function is going to be also stationary with respect to all these quantities, the velocity field, the flux field, and the concentration rate field. So I have to do the optimization again between the C dot, but the C dot are roughly what we want. Well, no, sorry. The C dot and the J are linked by the mass conservation. Okay. The J is also linked by the Neumann boundary condition. The velocity fields, okay, I want them to be, okay, this is with the bars, it's not ideal, but the velocity is known as on the displacement part of the boundary, okay, where I impose the displacements and the velocity. So velocity has to be what is known here. So here it's what I did there. Okay, there should be a vector. I don't know. Sorry, I've got typos here and there. I will fix them. So there's supposed to be a vector here. Okay, so I've got optimization problem with constraints. I do the same thing as usual. Okay. Probably have something here. Yes. So I define my Lagrange function. This doesn't change from before. Again, I skipped a little bit the details, it's too late anyway, but okay, stationarity with respect to velocity, I'm going to retrieve the conservation of the virtual power. Okay, very different you've done before. And for the rest, it's going to be roughly the same thing. Okay, we could spend also 10 minutes on writing the equations, but I'm going to get an idea from the. It's really similar to what we've done before. There's nothing new there. Okay, so this is this solution. This is the solution. Okay, so now we have a directional principle for the evolution problem. Okay, so now, okay, with all this now I can say yes. Constraint problem. Okay, now I've seen that every time the Lagrange multiplier is the chemical potential. Okay, so let's not pretend anymore and just say okay, yeah. Lagrange multiplier is the chemical potential, so let's make it an unknown. Okay. And then I can rewrite directly the Lagrange functional. I write it now, I replace lambda by mu, and I treat mu as a physical quantity, not a mathematical object which enforces the constraints. Okay. So this is just that, where I replace lambda by mu, because I've seen that lambda every time is the chemical potential field. Okay. So I try to get a more physical interpretation. Okay. And I'm saying that, okay, I'm in a given state, I know the current displacement and current concentration, and I want to find the velocity field, the chemical potential field, the flux field, and the concentration rate field. Okay. So some of these are a bit trivial. The mu, for example, in this case, the variation with respect to C dot is going to tell me that mu is the mu given by psi. Okay, it's a bit trivial, but formally you can write it. Okay. And so on. Okay, so you will, if you write this, you will receive all the equations that you are expecting. Okay. So it starts to become a bit heavy. Okay. If I wanted to actually use this, I need to have I don't know, like nodal. I need to do. If I want to find elements. Okay, I want to have something which is a function of. To have nodal velocities, nodal chemical potential, maybe nodal fluxes, nodal concentration rates, and do a finite element discretization of this. Okay, and this is the evolution problem. So it's not exactly what I want, but okay. So but I could do it. Okay, so I can also simplify it a little bit. Okay, these are a bit too much. So fluxes. Okay, I can get rid of them. Okay, so if I sorry, here, yeah. If I'm here, okay. If I isolate the optimization, the minimization with respect to J, okay. The only things which depend on J are these two terms, okay? So locally, so this J is a local quantity. If I know mu, and it's gradient. Okay, maybe this will depend on the state too, but okay. I want to minimize this, okay? So I need to solve this, okay? But this, if you go back to the duality between the dissipation functions, this is the definition of the differential transform between the phi and the phi stars. Okay? So actually this, we know that it's a Legendre transform, so this is how you construct the phi c. Okay? But okay, even if this is not a quadratic function, okay, this works. So I can replace this, so this eliminates the j, because the function which is not a function of j. And it reduces to this, so now I have a formulation which involves only the velocity field, the chemical potential field, and the concentration rate. I call this a three-field formulation. Okay. And in practice also, so again, for the moment I'm going to write a stat with respect to velocities because I have a linear terms in epsilon dot, so I don't know exactly. Okay, mu probably supremum. Okay, because it comes from, remember, mu was a Lagrange multiplier, but also this is quadratic, typically a convex function, but with a minus, so it's a concave function, so that makes sense to make a soup here. C dot, it's a linear function, so I don't know yet. So I put a stat, okay? And and it's going to depend in which order I do the optimization actually. Anyway, you could put stat everywhere. Okay, but, this one is very clear, so it's fine. Okay, so that's one thing. And then, if I look a little bit, mu, I've got gradient of mu here. Okay? So I need to know the field. The gradient, I need to know values in different points. Okay? In here, I've got the epsilon dot. So it's also a gradient of the velocity. So I need to know the velocity at the point, but also its neighbors to be able to compute the gradient. C dot, there's no gradient or any differential operator on C dot. It's local, okay? So it could be just like J, actually, just like J. So I could possibly solve this locally, okay? And develop this next time, but this is something local. I could make it a function, I could eliminate the C dot actually. Okay, make this a function of mu on the, I think would reduce even more the problem, and then we would get back on the chemical version, chemical potential version with displacement that we got before. But, this I'll do next time to show you the transition. Okay. So you have okay, all this variety of variational formulations. Okay. As always, having a lot of choice is always nice. But then you have to choose. And choosing can be difficult sometimes. Okay, so we are going to build on this, transform it to an incremental problem. That's what we actually want to do. We want to do time steps. And okay, from there, and we will see the connection with what we had before, and try to make also interpretation of this with respect to the numerical stability. Okay, I'll stop there for today. For this week. We meet next Monday. There's no course in Friday. So enjoy your lunch.